let's look at applications that deal with exponential functions. So we are going to talk about compound interest, and these are formulas that banks and financial institutions use. So let's see what these look like. So we have two different formulas. We have for compounding per year and for continuously compounding. So we are going to look at what each of these variables represent. So we have T years, the balance is A, principal is P, the annual interest rate is R in decimal form, and we are going to plug it into the formula. So let's go ahead and look at each formula. So compounding's per year, so in compounding. So it could be compounded annually, it could be compounded biannually, quarterly, monthly, daily. That is kind of what we're looking at there for the N. Continuous compounding is a completely different formula. N is the number of compounds per year, and T is the number of years. So we are going to look at a formula. So the first example that we're going to use a formula on is complete the table to determine the balance A for a $2,500 invested at a rate of R for T years, compounded N times. So we have the 2,500 is our principal, and it gives us the rest right here. We have R is 2%, so it'd be 0.02, and T is for 10 years. And then we need to look at what N is. So we're going to compare it all over a 10-year period, all at 2%. So 1, N being 1 means annual. So one time. Twice is biannual. 4 times is quarterly. 12 times is monthly. 365 times is daily. And then we have the continuously. So let's look at when N equals 1. We have A equals, we are going to use for this 1 through 365, we are going to use the first formula. P parentheses 1 plus R over N raised to the N times T. So the first one's going to be 2,500. 1 plus, we know the rate is 0.02 over N, so that'd be 1 raised to the 1 times 10. And when we put that in the calculator, it comes out to be 3,047.49. Let's look at when N is 2. A equals 2,500. The only thing that we're changing is the N. So 1 plus 0.02 over N, 2, and then 2 times 10. We'll plug that into the calculator. Comes out to be 3,050.48. Okay, let's look at when N equals 4. Same formula, 2,500. 1 plus 0.02 over 4, 4 times 10. Okay, that comes out to be 3,051.99. Okay, so go ahead and write down the formula and use 12. Plug in the 12. Okay, so hopefully you've already done it. So check it with mine. Okay. $3,053 whenever we have to round. So 3,053. Okay, now do daily. Okay, so let's see how you did. Okay, and I got 3,053.49. Okay, so they're all really close together. Earn a few extra dollars, but they're pretty similar. So let's look at the continuously. So that is a different formula altogether. It is A equals PE raised to the RT. So A equals 2,500. E, the rate, 0.02. Time is 10 years, so times 10. So put that into the calculator. So remember, E is a special function on our calculator, times E raised to the 0.02 times 10. 3,053.51. All right, so let's keep on going. Let's look at example 2. This should say 2. Find A, which is the balance for $12,000 invested at a rate R for T years compounded continuously. So this one we are going to use the continuous formula. Okay, our rate is 3.5%. So move that over 2 places. So our rate is 0.035. And we are doing it for T years, and we are compounding it continuously. So let's do when T is 1 year. So we're looking at after 1 year, what happens? So T equals 1. So A equals P E. Oh, I guess I should actually write the numbers, huh? Let me erase this real quick. So it would be 12,000 times E. Let's put our rate in, times 1. And that comes out to be 12,427.44. Okay, let's see, when T equals 10 years, 12,000 times E to 0.35 times 10. So go ahead and do these. I'm going to go ahead and write that down. And I want you to go ahead and do that right now. And let's see if we get the same thing. So for the 10 years, it's 17,028.81. Okay, let's go 20 years. 12,000. E, do our rate, 0.35 times 20. These are easy to change in our calculator, which is good. 24,165 and 3 cents. Okay, 30. 34,291 and 81 cents. Okay, and then 40. 48,662 and 40 cents. Okay, our last one is for 50 years. Wow, that's a long time to keep money in an account and for it to stay the same rate. If you know anything about interest rates, they fluctuate. So let's see what that would be after 50 years. How much would be in your account? 69,000, $55.23. So after 1 year, it went up about 400 bucks. But 20 years, it doubled. And then, wow, after 30 years, it almost tripled. And then 50 years, it almost was multiplied by 6. That's a lot if you can keep it in that account. All right, so that is just a little application for exponential functions for us.